Testing. Okay, good morning, student. Welcome to attend the theory of structure 2 again. This is the 7 lectures in this semester, around the middle of this semester. Well, before starting the lectures, there are 2 announcements I would like to let you know. Firstly, I received several requests from full-time and part-time students regarding to the assignment deadline. They would like to postpone the deadline for 1 more day. After considering their request, I would like to extend the deadline from today to tomorrow. So if you have not yet finished, at least you have 1 more day to complete assignment 1. If you have finished, then you can directly upload to Moodle and then you may have a rest during the weekend. Okay, this is the first announcement I would like to let you know. The second is about the quiz. Actually, I've mentioned at the beginning of this semester. The quiz will be scheduled in week 10 during the lecture period. The quiz will be in face-to-face mode. So you need to come back and have a quiz in the lecture theater. So make sure that you can access to this campus. Okay, you need to fulfill the vaccine pass, etc. Okay, face-to-face, no, not online. And last time, I think I mentioned that during the quiz, for the quiz or examination, I allowed you to bring 1 A4 paper. You can write all the notes, and you can write all the equations, example notes on both sides of the A4 paper. Okay, so if you can't remember all the equations, you can prepare the note sheet yourself and then bring to the exam venue. It may help you, I think. These are the second announcement I would like to let you know. Okay, the first one about assignment, second about the quiz in week 10. Today is week 7. Today is week 7. So 3 weeks after, we will have a quiz. The quiz will cover content from topic 1 to topic 5. Topic 5, we just finished last time. So we have covered all the contents for our quiz. So maybe it's a good time for you to review all the contents. Last time we finished topic 4, formulation for dynamic problem, and topic 5, free variations. Suppose today we will start from a new section, topic 6, forced variations. The difference between free variation and forced variation is that the free variations, there is no force, no external force. The structure can oscillate because you give them some initial conditions. You display the structures horizontally at the beginning and then release it suddenly, and the structure will oscillate back and forth. Free variations. Forced variations mean they are really dynamic force applied on the structures. So the structure will move, oscillate. But before entering a new topic, I think we may have a tutorial section first, that you have some idea what we will encounter in topic 5. And I think it's also one good way to review our contents rather than just go through all the notes again. During these tutorial sections, you can have a look of the problem type and the format of the questions. Before moving on to our tutorial 5 sections, is there anything you want to ask me? One more thing. This is week 7, right? I remember that next week, week 8, we have another round of workshop section on Thursday evening. We have another round of workshops on the next Thursday evening. So if you want to know more about SAP 2000, maybe you can also join our workshop on the coming Thursday. Again, the attendance is not required, but if you want to learn more, then I encourage you to join our workshop. I will upload the SAP 2000 assignment very soon. If you know how to use SAP 2000, then you can complete the SAP 2000 assignment easily. Just build a top building, calculate the top drip, quite similar to what we did in our workshops. So I believe that there's no question, right? I wait for a few minutes, but seems there's no response. So I assume that there's no questions. Again, if you have questions, you feel free to raise your questions by putting your questions on the meeting chat room, or you may directly speak out in any language, Cantonese, Chinese, it doesn't matter, okay? You can directly speak out. I can understand both. 有問題咁隨時提問啦，咁就 So if no questions, then I will go to tutorial 5. There are a few questions in tutorial 5. Let me share the screen with you. Tutorial 5. Oh, I should put the 5 here. But anyway, this is tutorial section for free vibrations. We successfully finished all the discussion for free vibration last time, topic 5. So it's good to have some examples. Free vibrations. Before going on to the example sections, there are a few slides to summarize what you have learned in topic 4 and topic 5. These are maybe some new things to most of you, structural dynamics. But firstly, in topic 4, we derived the equation of motion together using Newton's second law, using the D'Alembert's principle. There are different ways to derive the equation of motions. If you read the textbook, some textbooks also show you how to use energy method to derive the equations. But anyway, no matter what methods you use, for a single degree of freedom system, finally, you will get this equation of motion. mu double dot plus u dot plus ku equal to the external force. Last time we derived this using Newton's second law. Graphically, it means that for a single degree of freedom system means you have only 1 degree of freedom, like the horizontal displacement, u. A dynamic system governed by only 3 parameters, the mass, m, and then the damping coefficients. Damping coefficient is a number that used to take account of the energy loss, energy dissipations. It's a very highly simplified model because in the real building, we have many energy dissipation mechanisms, heat loss, friction, whatever. But we just use a single number to imitate this as just like a grouping all the effects together into 1 single coefficient. And then the last one is the stiffness. Stiffness is the same as what you learned before, just like a spring. Stiffness, elastic properties. You can calculate stiffness using the main property EI and their geometry, the length. Last time we showed you different models, rigid beam, flexible beam, etc. The right-hand side is the external force. So graphically, for a single degree of freedom system, they normally express using this kind of ball and stick model. For rigid beam assumption, K column is equal to 12 EI over H cube. For flexible beam, 3 EI. These are the 2 boundaries. In reality, the column stiffness should be somewhere in between the middle, but for easy calculation, normally we take these 2 boundaries. We also introduced 2 models, parallel model and series model. Just like these structures, normally you have more than 1 column, more than 1 members in the structures. So when you formulate this equation of motion, you have to calculate the total stiffness or the equivalent stiffness. Last time we borrowed our old concept in high school physics, parallel and series. So for example, if you play with rigid frame structures with multiple columns, with more than 1 columns, under horizontal force, all columns display horizontally with the same displacement. So according to our physics, this is so-called the parallel model. You can calculate the stiffness by adding up all the stiffness together, K1, K2, K3, and K4, and so on. The other case is in series. In series, I also showed you the scenario. Last time we had 1 problem talking about vertical vibration. We have a spring, we have a beam. At the end, there's a spring attached to a mass, something like that. This is classified as in series. For series model, you can calculate the equivalent stiffness using the formula at the bottom right-hand corner. So you can based on your structures, based on your model, calculate the equivalent stiffness and put it into this formula. Then you know the dynamic properties, MCK, very well. And then in the next topic, topic 5, we introduce free vibrations. Free vibrations mean there is no external force. There is no external force. But we have to give the structure some initial conditions. It can be initial displacement. It can be initial velocity. Display the structures away from the equilibrium positions at the beginning, and then let them oscillate without any external force. We solve the equation together, and finally we get this solution. When you answer the question in the assignment, quiz, or examination, you can directly use this kind of equation. You don't need to prove them to me. You can use it directly, as long as you use the correct formula, correct equations. This equation, A cosine, B sine, exponential function, this one is for free vibrations. Today, later, you will learn more and more equations for different scenarios. So pick the correct equation according to the problems, according to the questions. This one is for free vibrations. If you're good in math, then when you take a look on this equation, then you know how it's oscillate. Actually, this sine cosine can be combined into one cosine function. And then this rho is a Greek symbol talking about the vibration amplitude. And exponential function control the decay here. The amplitude will decrease as time goes on because of energy loss. So you will see that the structure oscillates back and forth about the equilibrium positions with amplitude decrease as time goes on. There are two curves on this graph. One is undamped, the other one is damped. Damped is more realistic because we have damping all the times. Undamped is just for discussions. It's not that real. You can calculate the coefficient A, B, using the equation on the right-hand side. They depends on what? They depends on initial displacement, initial velocity, U dot, depends on damping ratio. I hope you still remember what is damping ratio. And omega n. Omega n is so-called the natural frequency, one very useful parameter. Omega n, natural frequency, depends on K, depends on mass. Natural frequency depends only on this property, K and M. And then omega d. Omega d is damped frequency. We normally assume that they are the same. Omega d equal to omega n. You can also make these assumptions. So these are the things related to free vibrations, the basic solutions. If I ask you to find out the free vibration response, then this becomes the answer. But for sure, you have to find out what's A, B, or the other parameters. Okay. And then near the end of topic 5, there is one application about log decrements. We can use the outcome of free vibration to evaluate the damping ratio of a system. Damping is a very complicated mechanism. There is no any theoretical formula to calculate damping directly, different from stiffness. For stiffness K, you can calculate stiffness using ER, using length. But damping ratio seems there is no any easy way to calculate damping. Alternatively, you can use this kind of displacement response to evaluate damping. This is the free vibration response for a system that under considerations. You excite the structure so that the structure under free vibration using your own way. Excite the structure using your own way, and then measure their displacement history. Probably you will get a graph like this. Then how to calculate damping ratio? You consider their vibration amplitude, the peak, any two peaks. Say for example, U1 or U3, any two. And then record the time of occurrence, the time in which they achieve their maximum value, T1, T3. And then you can use this logarithmic decrement equations to evaluate damping ratio. Here I express the things in a very general manner. I use two any peak, peak I and peak I per j. But for your application, you can use any two. Using two amplitude, then j is the difference, right? The difference in terms of the number of cycles. Then you can evaluate damping based on displacement. Then you can understand the dynamic properties, again, MCK. This is how you can use lab to measure damping, measure the dynamic properties of a system. Okay, after our short revisions, there are some examples we can go through all together. I will give you some time to think about what to do for each question. Say here, question one. Question one: consider a single degree of freedom system. When you see this term single degree of freedom system, then you have to find out the corresponding dynamic components, MCK. For single degree of freedom system, it's very nice. It's described by only 3 properties, MCK. In these questions, I give you all these numbers. MCK, mass is 4.5 tons. Be careful about the unit. Be careful about the unit. Last time I mentioned about the unit. C is damping coefficient, 5,000 Newton second per meter. K is stiffness, 750 kilonewton per meter. One interesting thing. You know the units for M, mass, you know the units for stiffness, right? Force per length, stiffness. What about the unit of C, damping coefficients? We saw this term, damping coefficient, in topic 4 at the time when we discussed a concept called viscous damper. According to the idea of viscous damper, the damping force is linear proportional to velocity through a coefficient called damping coefficient C. From this equation, you know the unit for force. Force, you can use Newton or kilonewton, right? Velocity, you also know the units of velocity. Velocity, you normally use meter per second. So according to this equation, you can understand the unit of damping coefficient C, right? Newton second per meter, or you can use the kilonewton or km, up to you, okay? Force over speed, the units of C is something like that. Okay, continue to have a look at the questions. The system is subjected to 3 vibrations with initial displacement 0.1 meters. Initial velocity 0.5 meter per second. In these questions, you are asked to evaluate 2 things. Firstly, the vibration amplitude. If you still remember, the structure will oscillate up and down, back and forth. So you have to find out the amplitude. And question 2, part 2, you're asked to find out the displacement at time equal to 1.2. Time equal to 1.2. So you have to determine the displacement function. We give you in the notes, and then put time equal to 1.2 seconds, something like that. Okay. I give you a few minutes to have a look at the questions. You may also think about the procedures, what to do, which equation should be applied, what parameters should be calculated, something like that. I give you maybe 2 minutes. You may think about how to play with these questions. After that, we will go through the solution together. Example 1. This one is very straightforward, right? Directly asks you to evaluate the free vibration response of a single degree of freedom system. Actually, our revision section at the beginning showed you the answer already. You may go to page 3 right here. Page 3 shows you the free vibration response U. And also, you can calculate the vibration amplitude rho easily. Based on the number A, based on the number B, you can evaluate the values of rho. You can follow the equation for rho in our lecture notes. I'm not put in here because there will be too many equations if I put all the things on this line. You can find out the equation, the formula for rho in the lecture notes. It depends on A and B. Rho is equal to square root A. Rho is equal to square root A squared plus B squared. So if you know A, if you know B, you can calculate this number rho easily. And then part 2, displacement function. Actually, this one, A cosine B sine exponential function. So all the answers are actually right here. You can directly use the formula, but you have to give me the number. What is omega n? What is omega d? What is A? What is B? Etc. You know the initial conditions. Point 1 for the initial displacement, point 5 for initial velocity. So direct substitutions. In example 1, we are playing with free vibrations. Free vibrations mean we have no force. Normally, I put down the equation of motion to understand the problems. No force, free vibrations. I can use this formula directly. For free vibrations, the displacement should look in this way. A cosine B sine times exponential functions. There are two forms, right? In the notes, we mentioned that there are two forms. You may use the traditional form, A cosine B sine, or if you like, you may use the alternative form, rho cosine something. Depends on which one you are more familiar with. Both equations, I will give you full marks if you use either one of them. Doesn't matter. I put down all on the solution, but you can use just any one, either one. And then fill in the blank, find out what is A, what is B, what is omega D, what is omega n. Natural frequency, according to our discussion, natural frequency depends on K, depends on mass. When you calculate natural frequency, pay a great attention to the unit. Make sure that the units are consistent. Normally, I change all the units to standard unit. Force, I use Newton for force, meter for length. I use kg for mass, for example. Normally, I change to standard units so that avoid any chance to having error about unit conversions. But you may use your own way. Okay, you may use your own way to do the calculations. Natural frequency, 12.91 radian per second. Radian per second. Natural frequency is measured using radian per second. How many rotation in radian per second? Omega d is approximately equal to omega n. We can always keep using this assumption. Damping ratio. Damping ratio is appeared in the equation, so I also calculate the values. By definition, damping ratio is equal to C, damping coefficients, over critical damping coefficients. Critical damping coefficients is equal to 2m omega n. When you read the lecture notes, then you can see this formula. Here I directly use the formula, C over 2m omega n. By definition, damping ratio, the ratio between the damping coefficients to a critical number to see if there's any oscillation. Right? We have overdamp, underdamp. For most of the structures, we belong to underdamp scenario. Damping ratio less than 1. Underdamp scenario, damping ratio less than 1. Then when you will start to see oscillations. Normally, the damping ratio for a structure is a few percent. 5% for RC structures, normally. Then again, put all the numbers into the equation. C2m omega n, you can find out damping ratio. 4.3%, 3% is more. So we know omega d, we know omega n, we know damping ratio. It seems that the missing thing is AB or rho, depends on which form you are using in your answer. In the next line, I just again substitution. Find out A, B. A depends on initial displacement, or 1 given. B is slightly complicated because it depends on speed, depends on damping ratio, frequency, and also the initial displacement. It depends on more number. But I believe that you should have no problem for these substitutions. Then you can find out B. If you know A, if you know B, then you can find out rho. Rho is one thing you have to calculate in this question, part 1. Approximately 0.11 meters. Theta is the phase angle. If you use the alternative form, then you have to also find out theta. Minus tangent, arctangent B over A, minus 0.406 radian. And then I substitute all the numbers back to our alternative form. So we have the displacement function for this system. Part 2, you are asked to find out the displacement at time equal to 1.2. So you can substitute t equal to 1.2 into the equations. Minus something. To make the things more clear, I suggest that you may also plot this equation in using the Excel to see how the structure oscillates with respect to time. At time equal to 1.2, here is 1, here is 2. 1.2 is approximately, I think it's here, something like that, in the minus region. It seems okay, right? A very direct applications of our solution, free vibrations. You understand how they change with time. Example 1. Example 2. We increase our difficulty a little bit. This time we consider a structure a mass supported by 2 steel plates at the beginning. You can imagine that if the 2 steel plates remove suddenly, this mass will going to fall down due to gravity. This structure is under vertical vibration, not horizontal. So according to our discussions, when you consider vertical vibrations, you have to consider the sub weight because of the gravity field, gravity accelerations. But this mass will not fall on the ground because it's attached by a spring, by a damper. So after some movement, the structure will go up and go down, go up, go down periodically. You can see that actually it's under some oscillations. Then what we're going to do, in these questions, we are asked to determine the displacement function, U. How is oscillate with respect to time, U. Assume that the spring force is 0 at the beginning to make things simple. No deformation for the spring. We set this as our reference level and initial displacement, U bar. U bar is displacement. I just put a bar here because there are many symbols for dynamic problem. So sometimes we put a bar to distinguish 2 different meanings. Displacement measured from this initial position is denoted by U bar, 0. Initial velocity also 0 because this mass is sit on this steel plate without any movements at the beginning. Again, I give you maybe 2 minutes. You can think about what to do. Can we apply the free vibration response on these structures? You can think about these questions. Can we apply the displacement function U for free vibration for this problem? You can think about this. As I mentioned before, you have to use the equation appropriately. Think about the criteria for using our free vibration displacement equation. What is free vibration? Free vibrations mean there is no force, no external force. Is there an external force on the structures? If no, then you can use it, right? Otherwise, you cannot use it if there is force. And the idea? Displacement function. Can we use this equation directly? We can't use it, right? Because this equation is valid if there is no any external force. But in these questions, we have external force due to set weight, mg. So the net force is not, the external force is not equal to 0. We have external force. So theoretically, you cannot directly use our free vibration response for this problem. But if you remember, last time in topic 4, we have one particular section in topic 4 talk about how to deal with vertical vibrations. I think it's topic 4, section 3, I think. We discussed how to deal with vertical vibrations. In this example, I will use that approach to deal with structures under vertical vibration so that we can apply the formula that we learned before for free vibrations. Let's have a look how to use the trick to deal with vertical vibrations. Well, for structures under vertical vibrations, it's good to derive different displacement descriptions. Just like this picture, at the beginning, we measure our displacement at undeformed level right here. Undeformed level. According to the questions, I use the symbol U bar to denote the displacement of the mass measured from the undeformed positions. U bar. And then in the notes, I use another symbol, U, to describe displacement measured from another reference level. This reference level is called static equilibrium level. Why we have static right here? You can think about the scenario. When you let this mass oscillate vertically, the oscillation will finally at rest as time goes on because of energy loss. You have damping, right? Because of energy loss, the mass will finally stay at rest at one level. So it becomes static if the mass does not move as time goes on. Then what is the distance away from the undeformed positions when it's achieved in static conditions? Now, there are two resistance, right? There are two resistance. One is provided by the spring. The other one is provided by the damper. There are two resistance against the set weight. There's mg at the bottom. And you can see the damper. Damper has no contribution for static because damping force depends on the speed, but the structure does not move at time equal to, at the static conditions. So the damping force has no contributions. It seems that only the spring force help to resist mg. Only the spring help to resist the set weight at static conditions. That's why you can find out the static level using this simple equation. K time distance, the displacement, equal to set weight. I move the equation a little bit. Mg over K give you this static level as time goes on. Okay, this is the meaning of this static displacement due to its own set weight. And then we can measure our displacement from our static equilibrium. I use a symbol U. This is a very useful technique to deal with vertical vibrations, and you will see very soon on the next page. There are two displacements. One measured from initial undeformed position. The other one measured from static. They have a relationship. U bar equal to U plus delta ST. From the graph, you can see this easily, right? Equation of motion. Equation of motion here I derived using this Newton's second law again. We have two resistance. Damping force, elastic force, mg, external force, and we have ma, right? A typical equation of motion. The external force PT, external force is equal to mg because we have set weight when you talk about vertical vibrations. So as I mentioned at the beginning, this is not a free vibration. When you just take a look on this equation, you have a constant force on the right-hand side of the equations. So it seems that we cannot directly apply our previous formula for free vibration. Right-hand side is not equal to 0. But there is some trick can change this equation to free vibrations. How? Using the static condition, using our displacement u. How? These equations we just mentioned on the previous slide, differentiate this equation with respect to time, you can find out the velocity and accelerations. We try to correlate u bar and u, and then we replace the equation from u bar to u. This is a trick that we normally use for vertical vibrations. Originally, we described the equation of motion using u bar, using the undeformed positions. And then we can replace u bar by u later. Dr. Till, the relationship to the equation change everything to u. Stiffness. K u bar can be replaced by K times u plus delta st. The right-hand side is mg. But when you take a look on the static conditions, K delta st equal to mg. So after these cancellations, you can cancel K delta st and mg, right? After this cancellation, you can see that, oh, the equation, force becomes 0. Force becomes 0 means it is under free vibration. Mathematically, this is same as just like horizontal vibrations. For this form of differential equation, you know the solution. The solution is the free vibration response. A cosine, B sine times exponential function, that one. So after this translation, we can translate a structures under a constant force. You can translate a structures under constant force to free vibrations in terms of something like mathematics. But this one, you can see that the displacement is now measured from the static equilibrium position, not the undeformed level. So you have to pay great attention. U is now measured from static, not the initial one. Okay. So for this form, we know the solution. The solution is this one. Rho cosine omega t plus theta times exponential function. We know the solution. You can put it directly. But again, you have to find out the corresponding number. What is rho, what is theta, what is omega, what is blah, blah. You have to find out the remaining numbers based on the given informations. Normally, in the quiz examination, I will give you some numerical values for mass, for stiffness, for the other thing else. So you can find out the exact number normally in the quiz examinations. But when you read the example in the notes or in some textbook, sometimes they deal with this kind of symbolic operations. Okay, how to find out the coefficients? The coefficients, if you remember, the coefficient depends on initial conditions, initial displacement, initial velocity, that kind of things. In the questions, at the beginning, I give you two initial conditions, u bar 0, u bar dot 0. They are the initial conditions described using u bar. U bar means the displacement or velocity measured from these undeformed positions. Right? We know the initial conditions described using u bar. But now in the equation, we are using u, not u bar. So you have to convert the initial condition from u bar to u again. You have to convert the initial condition from u bar to u. U0, u log 0. How? Don't think it's not that complicated actually, because you know the relationship between u bar and u. You know the relationship between u bar and u. U bar at time equal to t is equal to u at time equal to t. plus delta ST. You just substitute T equal to 0 into this equation. Then you can correlate the initial conditions described using U bar and U. I think I put the formula on the solution right here. You know the relationship between displacement and velocity. So you just put T equal to 0 here, T equal to 0 here. Then you know how to translate the initial conditions from U bar to U. U bar 0 equal to 0. U bar dot 0 equal to 0 according to the problem. So you can find out U0 and U dot 0 easily. This is what I do here. Just simple substitutions. I found that U dot 0, the initial velocity equal to 0, while the initial displacement U0 is equal to minus mg over k. U bar 0 equal to 0. So delta ST plus U0 equal to 0. Move delta ST to the right-hand side of the equations. Then you have these expressions. The initial conditions in red color here and this one can help you to evaluate our coefficient rho. Rho depends on initial conditions. So you can put the things into the formula. There are some simplification at the bottom. When you answer the problem in quiz or examination, if you're not good in math, if you're not very good to doing this kind of simplification of the formula, then you can just put down the formula and tell me what is U0, U dot 0, omega, etc. Okay, you can ignore these simplifications if you don't good in this math. Just let me know what is rho, what is initial displacement, initial velocity. If you're good in math, then you can do a little bit calculation to simplify the expression, make it look better. Here we found that the vibration amplitude rho is equal to mg over k, approximately equal to this number. So if you like, you may put it into the formula. Then what is the total response? Total response means U bar measured from the undeformed positions. Again, use the same definition, U bar equal to U plus delta ST. So if you want to know the response of the mass measured from the undeformed positions, then this becomes the formula. This becomes the formula. If you want to know the displacement of the mass measured from the undeformed level, measured from here, then the solution becomes this one. There's one constant before the free vibrations. Okay? You can observe from this equation for a system, for a single degree of freedom system under a constant force. Say, for example, under a constant force mg or a constant applied force. Okay? Under a constant force, mg was due to the other effect. Constant. The constant force will make the solution composed of two parts. One is a constant displacement. The other one is a free vibration response. So you can also observe from this example about the solution. If you get in math, then actually if the right-hand side is not 0, in our differential equations, we call that non-homogeneous equation. For non-homogeneous equation, the solution should compose of two parts, particular solution and homogeneous solution. So you can understand physically or mathematically, I think. I think this is the last example in this notes. Example 3. Example 3 is maybe I think is the more complicated example. This one is related to free vibration test. In the notes, topic 5, near the end, we mentioned that we can use free vibration to determine our dynamic response, dynamic property, dynamic characteristics, MCK. This example is actually talking about that kind of free vibration test. I will go through the question one time, and then I will also give you a few minutes to think about what to do. Let me go through the questions to let you know what you are doing. In example 3, we assume that there is one-story building. Assume that it can be idealized at rigid beam. assumptions. Raceless column. So all the masks are basically due to the slab. We are asked to evaluate the dynamic property of these structures. Dynamic properties mean MCK. MCK, these three. They appeared in our equation of motion. We would like to evaluate our dynamic properties for these structures, MCK, using a free vibration test. How to excite the structures to undergo free vibrations? This question tells you the answer. How to make the structure under free vibrations? Well, in laboratory, you can display the roof level of the structure laterally by a mechanical system called hydraulic jack. Hydraulic jack is a mechanical system in lab. They apply a force, push the structures horizontally. Okay, in the lab you can apply a force on the top of structures, make it display horizontally at the beginning. Display how many? It is observed that the force is 88,996 Newton. You apply this force at the top of the structure at the beginning, and the structure display horizontally by a distance of 508 cm. You push the structures horizontally by a force given right here, and the structure displayed by this number at the beginning, time equal to 0 at the beginning. And then you release the force suddenly. You release the force suddenly from the initial displacement. You allow the structure oscillate under free vibration. You remove the force. The structure will undergo free vibration. Firstly, go here and then go back. Oh, not go here. I draw the wrong arrow. At the beginning, the structure is located right here. It will be bound back and then go to the same side again. Oscillation, right? After one complete return cycle, after one complete vibration cycle, when the structure returns on the same direction, same side, then we observe that the new displacement dropped to 0.406. The displacement dropped to 0.406 cm after one vibration cycle. The reason is very simple, because of damping, right? Because you have damping, so the displacement reduced after one vibration cycle. And we record the time. We found that the structure takes 1.4 seconds to complete one vibration cycle. These are all the information we have. What we are going to do? We are going to evaluate the dynamic properties. Mass. I also wanted to find out natural frequency, one important parameter, and then find out damping ratio, find out damping coefficient. Damping ratios mean this grid symbol. Damping coefficient means C. Find out damping properties. And then finally, try to estimate the amplitude after 6 vibration cycles. This is different from the previous two examples. Now we are playing with a free vibration test. Try to use the test data to determine MCK. Similarly, I give you some time, maybe 2 minutes. You may think about what to do. This one is quite different from the previous two examples. There are many information given in the questions, but please note that some information may be useless, may be redundant. Not all the informations are relevant. Okay, let us have a look of the solution together. Determine mass, determine natural frequency, determine damping ratios. This is the order that I give you in the questions. But when you answer the questions, it doesn't mean you need to follow the order 1, 2, 3. You can answer whatever you know. Just mark the question clearly on the answer book. When you take a look on the problem, there is one very trivial information. This number, the time required to complete one vibration cycle. What is the meaning of this number? The time required for one vibration cycle means the period. Period. Period of a structures. If you know the period of a structures, period is related to our natural frequency through this formula. 2 pi over omega n equal to period, or omega n equal to 2 pi over period. So actually, you can find out part 2 at the beginning, natural frequency, because you know the period. And then there is one very interesting information, the force. At the beginning, you apply a force 88,000 something, and the structure display horizontally by this number. This information tells you another useful structural property. What? Just like a spring, you pull this string by a force, and you know the displacement delta. Using force and delta, what you can obtain? You can obtain stiffness. Just like these structures, you pull this structure by force, and then you know the displacement. By using these two information, F and D, if I just call this D, by using F and D, you can find out delta, I use delta in this picture. By using force and delta, then you can evaluate thickness. So don't be misled by the problem. Although I mentioned that the beam is rigid, but because you have no idea about the column fracture rigidity, you have no EI of column. So the rigid beam assumption is not very useful in this problem. But you can use the lab data to measure stiffness K. So you can find out omega, you can find out stiffness easily. Then what about the mass? It's testing you the understanding of the formula. Right? Omega n, by definition, omega n is equal to square root K of m. If you know K, if you know omega, it seems that you can find out mass. You can also find out the mass using the period. Depends on where you start from in this problem. Okay, that's why using all the properties, you can find out frequency, find out period, find out stiffness. So part 1, part 2 can be evaluated directly. Damping ratio. Damping ratio. How to calculate damping ratio from free vibration test. In the notes, we discussed one concept called logarithmic decrement using the displacement response of free vibration to find out damping ratio. You can use that one. You know the displacement result. I give you 2 displacement at the beginning and displacement after one cycle. So if you plot the displacement graph yourself, actually the graph will look in this way. At the beginning, 0.508. After one complete vibration cycle, here, 0.406. And then you can use the logarithmic decrement equations using 2 adjacent vibration amplitude to find out damping ratio. So it's not that difficult right here. Okay, this is how we can find out the 3 dynamic properties, MCK. in this question 3. Let's have a look at the solution to see the numerical values. We mentioned the concept here, but how about the numbers? Well, stiffness, you can evaluate stiffness directly. As I mentioned, you know the force, you know the displacement at the beginning. So using stiffness equal to force over displacement, you can find out stiffness. 17.52 times 10 power 6 Newton per meter. I use Newton per meter for the unit. If you like, it may change to kilonewton per meter, something like that. Mass. I calculate mass first in the solution. Mass, we understand that period equal to 2 pi over omega, where omega equal to square root K over n. Omega equal to square root, omega n equal to square root K over n. So when you combine the period equation and omega equation together, you can see that period is equal to 2 pi square root m over k. Change the equation a little bit. We arrange the equation a little bit. Move mass on one side, move the other items on the right-hand side of the equation. We know period. Period is 1.4 seconds. Stiffness we just calculate at the top. So when you put the numbers together, it becomes our mass. 870 tons, or you may use kg. So you know mass. We know mass. We know stiffness. But unfortunately, the question also asks you to find omega. So there's one step here. Find out omega n. You can calculate omega n using period, or you may calculate omega n using square root m of k, square root k over m. Depends on your own preference. Because right here, you know stiffness, you know mass. So actually, you can calculate omega using the definition, square root k over m. Or you may use period to evaluate omega n. This is part 2 for this problem, lateral frequency. Just again to recap the concept, how to calculate frequency. Damping property. Damping property, you can use the log decrement equations. Because you know the displacement graph. You know the value at the beginning. You know the value after one complete cycle. So here you can easily use log-confirmed decrement operations. I firstly calculate lateral log U0 over U1. U0 is 0.508. After one cycle, the displacement dropped to 0.406 according to the problem. They are different by one cycle, adjacent to each other. Take the lateral log first, and then put it into our damping equations. When you read the notes, the equation should be something like this: 1 over 2 pi lateral log ui over ui plus j. There's a j here. This is the formula that you find in the notes: 1 over 2 pi j lateral log ui over ui plus j. Here, j is 1 because they are different by one cycle. J is 1. So damping ratio is equal to 3.55%. Small damping. We know damping ratio. The question also asks you to evaluate damping coefficients. Damping ratio and damping coefficients, they are related to each other. Recall the definition of damping ratio. Damping ratio is measured the ratio between damping coefficient to a critical number, 2m omega. So if you know one, you can evaluate the remaining damping numbers. Here we know the damping ratio. You can see that damping coefficient C is equal to 2m omega times damping ratio. That's why you can evaluate C easily. You know mass, you know frequency, you know damping ratio. The unit, I mentioned unit in question 1 already, force over speed, Newton second per meter. Okay. Be careful about the unit for damping coefficients. So we know damping. Now we know all the parameters M, C, K. We understand all the dynamic properties for these structures. So in the future, if the structure is under any dynamic force, side force, ground, earthquake, ground movement, wind force, any dynamic force, based on this property, you can evaluate the response. You will learn how to deal with those force vibration in the next topic, topic 6. But at least this gives you some idea how to find out dynamic property of a structures. Sometimes you don't know the member property, so you can also use this kind of idea to find out their property. There's one last question. Find out the amplitude after 6 complete cycles. After 6 complete cycles. Well, here you can use the log-decrement equation again. This one. You can use the log-decrement equation again, but this time J is not equal to 1. Right? You put J equal to 6 after 6 cycles. Then you will see what happened after 6 cycles. This equation is also quite useful to understand the new displacement after n cycle. Right, you put J equal to 6. Put J equal to 6. You know damping ratio. You know the initial displacement, U0. You just need to find out U6. Then by doing the calculation using our calculator, then it seems that the displacement after 6 cycles is equal to 0.133 cm. Drop to 1.133 cm. Okay, these are all about our tutorial 5 for free vibrations. I hope the 3 questions help you understand the possible questions that you may encounter. We handle question 1, question 2 about the direct application of the formula using free vibration response. In question 3, it's quite different. We use a lab to find out the dynamic properties. So let's have a short break for 5 minutes. And during the break, you may also have a look of the solution again to see if there's any questions you want to ask me. Testing. Okay, let us continue our discussions. Before the break, we mentioned one document, tutorial 5, regarding to free vibrations. The next part, we will move to another new topic, topic 6, to talk about what happens for a system under forced vibrations. If there is a dynamic force, then how to solve the problems. Before that, I would like to remind again three things. We postpone the deadline of assignment 1 to tomorrow. So if you have not finished, you still have at least 1 day to finish assignment 1. And then we will have a quiz on week 10. Yeah, face to face. Make sure that you are able to come back. You can bring one A4 paper to put the example or formula that you think are useful to you. Okay, you can bring an A4 paper. You can write anything on both sides of the A4 paper. One A4 paper, 2 pages. You can put down example, equation, formula, essay, whatever. And then next Thursday, we will have another round of workshop SAP 2000. We finished the first one in week 5, and next week, week 8, we have another round. So these are some announcements for we mentioned at the beginning of this module. I just repeat. So any questions you want to ask me? 有冇問題？ Well, if no questions, then we can move on to a new topic, topic 6. This is a new topic, topic 6. The title is forced vibration. In this topic, we also focus on single degree of freedom system, but this time external force is not equal to 0. This time we have dynamic force. Normally we call this forced vibrations. Let us have a look at the descriptions. Forced vibrations or forced excitations. We consider a single degree of freedom system, which is characterized by NCK, the 3 dynamic properties. This time we have a dynamic force P applied on the structures. So P is not 0. P is not 0. We have something on the right hand side. Mathematically, we call this second order non-homogeneous differential equations, which is the solution composed of 2 parts. The solution U depends on the function of the external force. Then what kind of external force we have? At the bottom, I give you some example. The most trivial, the most classical loading is we call it harmonic force or harmonic excitations. Harmonic means sine, cosine, something like that. We normally use sine. But in principle, you can also use cosine. But normally we use sine to describe the force. Sinusoidal force. The force is time dependent, depends on time. So it is a dynamic force. The other example is impulse loading, impulse force. The value is equal to P. P0 is a constant, the amplitude times delta function. Delta function is quite special. When you plot the graph, the force versus time graph, delta appeared only at one particular time instant. Delta only has a values. The value is equal to 1. delta function. Delta values has a number equal to 1, and has a value equal to infinity. At a particular time instant. For the other level, the magnitude is equal to 0. 0, 0. Only at one time instant, it has a large value. The area under this graph, under this bar, is equal to 1. The area under this bar is equal to 1. A very special loading. If you use this value, then you can see that it says the force appeared only at a certain level, certain time instant. The force appeared suddenly on the structures and then disappeared. Impulse loading. Reinforce wind excitations. Wind can be divided into mean wind speed and variation. So in terms of the wind force, wind pressure, you can also divide the wind pressure or wind force to the mean part, the average part, plus the time varying property. What I mean is that when you measure the wind speed, wind force depends on wind speed, right? The higher the wind speed, the higher the wind force. When you measure the wind speed, normally we found that the wind speed will oscillate above or below one mean level. We found that the wind speed oscillate above or below one mean level. So in terms of the force can be divided also into the mean part and the time varying part in terms of the nature. So wind force, if you want to get the precise answer, the wind force can be also modeled as dynamic loading, the mean part plus the dynamic part. But for our design, you will learn how to use Hong Kong wind code very soon in the next semester. In our design, we normally use some simplified method, treat the wind speed as something like a constant force to make the calculation more easy. Because for normally engineers don't want to consider too many dynamic effects. They will convert that to equivalent static. We will discuss how to do the calculation later. The last one is earthquake. Earthquake is dynamic loading, random. Earthquake is quite complicated. Random oscillations at the ground level. So here you have to model using dynamics right here. But again, there are some tricks to convert that to static. Depends on the time. We will mention harmonic and impulse loading. If we have time, maybe we can go to earthquake a little bit. Depends on our times. This is the contents. This is the contents of this PowerPoint, of this file. The content is that we firstly talk about harmonic vibrations. A sine force, simply speaking. And then we will go through the applications. There are several applications for harmonic vibrations. Some are quite useful. We normally use a sine force to discuss forced vibrations. And then we will move on to impulse loading and one useful technique called the Harvard integral, a very famous concept. Although it's difficult to apply, but very, very general. And then we go to pulse excitations. At the end, there is one chapter called periodic loading. At the beginning, we focus on damped harmonic excitations. When you read the textbook, some textbook will also show you undamped harmonic vibrations. But I think undamped is not that common. So here I directly go to damped harmonic vibration. If you want to know the undamped behavior, you may go to the textbook. Although I think it's not that realistic. So to save the time, I directly go to a damped single degree of freedom system. Under harmonic excitations, harmonic means sine or cosine. We normally assign sine function to describe the force. I put a graph to make you more easy understand what is sine force, as shown in the blue color. A sine force at the beginning, 0, and then increase to our amplitude, T0. And then the force drop to the negative directions and then increase again. psi force. The time to required for the force to complete one cycle is equal to T. I put a bar on the top to make it different from the structure natural period. This T bar is talking about the time for the force to complete one ribation cycle. Okay, it's talking about the force, not the structure. The structure itself has their own natural period. They are two different things. So this is the equation of motion. N double dot plus zero dot plus Ku equal to the force. The force is P0 sine omega bar T. Omega bar is called the excitation frequency, or you may call this loading frequency. Loading frequency is somewhere dependent on the vibration period here, the loading period here, T bar. Omega bar equal to 2 pi over the vibration period. Okay. The time required for the loading to complete one cycle, T bar. T bar and the loading frequency, omega bar, they are related to each other. T bar and omega bar. They're talking about the loading, not the structures. Omega bar, T bar, they are talking about the loading, not the structures. Structure itself has its own frequency. As we mentioned in the previous chapter, omega n equal to square root K over n. Omega n is the natural frequency of the structure itself under free vibrations, square root K over n. The loading itself has its own loading frequency, omega bar. There are two different numbers, so don't confuse. There are two different numbers. Depends on how you excite the structure. You can tune the frequency so that it is equal to the natural frequency if you like. But in general, omega bar is different from omega n. In general, it can be any loading frequency. Omega bar, you may call this exciting frequency or you may call this loading frequency, up to you. Exciting frequency or loading frequency. Natural frequency, omega n, square root K over m. They are two different things. After some introduction here, what we're going to do, as usual, we would like to solve this equation to find out the displacement. We want to know how the structure oscillates with respect to time when it is under harmonic loadings. To solve the problem, we also need some initial conditions, U0, U dot 0. Target solve for displacement, UT. In topic 5, we learned how to solve the equation under free vibrations with no loading. Here, we have force. So how to solve the problems? The problem definition is here. For a damped single degree of freedom system, we have our Garfunkel equations. We have initial conditions. This equation is so-called the second order non-homogeneous differential equations. For non-homogeneous equations, the solution will be composed of two parts: homogeneous part and the particular solution, two parts. The homogeneous solution simply means the solution for a homogeneous differential equation in which force equal to 0. Homogeneous means the force equal to 0. I call this homogeneous part as UH, homogeneous solutions. We have to find out UH first, but this one we has already handled in previous chapter, topic 5. Right? If force equals 0, which means you are talking about free vibrations. So UH is known, you know UH, free vibrations. UP, this one is called particular solution. Particular solution depends on the loading. For sine loading, you have one particular solution. For impulse loading, you have one particular solution, and so on. Particular solution depends on the things, the function on the right-hand side of the differential equations. So we have to find out particular solution ourselves. Particular solution. From the equation, you can see that it's involved second order, second derivative, first derivative of displacement, and we have a sine function on the right-hand side. So it's reasonable to use sine or cosine function to describe our particular solution. We use sine cosine function in our solution form here. The particular solution, we use sine cosine function. The reason is very simple. When you differentiate sine cosine, it will return back to sine cosine later, right? So if you put these back to these particular equations, hopefully you can make left-hand side equal to right-hand side, as long as you tune the parameter properly. When you tune the coefficients properly, then you can make right-hand side equal to left-hand side when you use sine cosine as the solution form. Now, one difference is that this sine function depends on the exciting frequency of the loading, omega bar. The sine function, cosine function depends on loading frequency, omega bar. And there are two coefficients, C and D. We have to evaluate it. I put the derivations on a few pages later. If you like, you may have a look at the derivation yourself. Here, I directly give you the expressions for C and D. It's not quite complicated. C, right here. D, right here. Later, we will do some conversions. So this is just for your information. Okay. Later on, we have more simplified expressions. C depends on P, the force amplitude over stiffness, and then 1 minus beta square plus 2 damping ratio beta. There are one new terms in these expressions. Beta. What is beta? Beta is another useful parameter that you have to remember. Beta. Beta is called frequency ratio. Beta is called frequency ratio. The definition is loading frequency divided by the natural frequency of the system. Omega bar over omega n. Be careful about the definition. Beta is divided as the loading frequency over natural frequency. Do not reverse the order, because later on, quite a lot of equation expressed using beta frequency ratio. If you reverse the definition, then it becomes another answer. So please remember this definition: loading frequency over natural frequency, omega bar over omega n. Particular solution: C sine omega bar plus D cosine omega bar t. Homogeneous solution. Homogeneous solution means take force equal to 0, which is equivalent to our free vibration response. UH is our free vibration response. We know UH, we know UP. So now you can put the two things together to form our general solution for our equations. Total displacement. Total displacement is equal to the homogeneous solution, UH, plus the particular solution, UP. This is the general solution for a single degree of freedom system under harmonic excitations. It's quite complicated, right? There are 4 coefficients, A, B, C, D. Some depends on the net damped frequency. Some depends on loading frequency. There are 2 terms to describe their physical meaning. The first part, the blue one, which is the homogeneous solution. We call that transient response. Transient response. Well, the second part, the red one, the particular solution. We call that steady state response. Steady state response. What is transient? What is steady state? Transients, for the blue part, you can see that there is one exponential function. There's one exponential function for the blue plot. Exponential function is a decay function. Decay means as time goes on, maybe go to infinity. This